this is Thinking Machines. In this section, we will be familiarizing ourselves with backpropagation, which is going to help us later when we talk about neural networks. First, let's recall what we have so far. Remember that in classifying images, we use a scores function or classifier to map pixel values to class scores. The matrix W contains the weights associated with each class, and the vector xi contains the pixel values of the image. If we have three classes, say airplane, car, and motorcycle, the scores function will tell us what class it thinks the image belongs to using matrix multiplication. Next, we have the cross-entropy loss, represented by this formula, that tells us how far off our guess is from the correct one. That is, we're trying to measure our unhappiness with the result of our scores function. Our goal is to have a loss as close to zero as possible. The third equation takes the average of all the losses from our training images and adds a regularization term to make sure that our weights are simple and do not overfit the training set. We'll get a deeper understanding of the regularization term in a later video. Now recall that we want to minimize the loss function, and we compare the process to walking down a mountain blindfolded, but we're only able to take a small step at a time in the steepest direction. Now, in order to move the output of our loss function in the direction of steepest descent, we need to take the gradient of the loss function L with respect to our weights W. In other words, we're making a parameter update to our weights. This animation shows how different algorithms find the global minimum by taking small steps in the negative gradient direction. The equation here says that to get the new weights, we move the old weights by some factor of the gradient. Here, the Greek letter eta denotes the learning rate. Take note of the learning rate as it affects how well your algorithm converges toward the minimum, although in practice, it might be tricky to find a good learning rate. Recall our earlier video on linear classification, where we came up with scores and determined a loss using the softmax classifier. We can generalize this whole process using a framework called the computational graph. A computational graph is a diagram we use to represent any function, and the nodes you see here are the steps in our computation. So x and w here are our inputs, and this multiplication node represents matrix multiplication that outputs the class scores. What else can we find in this graph? We have a node here that computes the cross-entropy loss, and the bottom node computes the regularization term. At the end of our computation, we take the sum of our cross-entropy loss and regularization term to get the total loss. Now, using this whole diagram, we can compute the gradient with respect to every variable in the graph. Although, in theory, we can use calculus to compute each gradient analytically, we will run into some trouble when we encounter exceedingly complex functions and convolutional neural networks such as this one. In this example, our input goes through many layers before it arrives at the loss, and it becomes less practical to compute the gradients analytically. A good alternative is to use backpropagation, which is a technique of computing gradients through recursive application of the chain rule. As we mentioned before, this will come in handy when we encounter neural networks of arbitrary complexity, because we use the gradient to perform updates to the weights W. For the next exercise, we'll be using these common derivatives from calculus. Feel free to pause this video to review this slide. To show how backpropagation works, let's start with this simple example. You are given the function f of x, y, and z equals the quantity x plus y times z, along with the given values x equals -2, y equals 5, and z equals -4. And we want to find the gradients of f with respect to each of these variables. We'll denote the gradients by partial derivatives. First step is to represent our function using a computational graph or a circuit diagram, and the key to creating a good diagram is to break the function down into its simplest variables and operations. So we have the simplest variables x, y, and z on the left-hand side. You'll also need to accurately illustrate the intermediate steps so that they reflect the correct mathematical sequence of going through the operations. We follow the PEMDAS rule, that's PEMDAS, for operator precedence. And using the nodes, we illustrate that we first add x and y and multiply the result to z, to compute for the final value. We also write the numerical values of x, y, and z here. Before we do backpropagation, we do a forward pass of the network, which means we go through the intermediate steps of computing for f. So looking at our function f, we know we should add x and y first. So given -2 and y equals 5, what is x plus y? We get 3. And we write 3 beside this node here. Then we multiply 3 by z, so 3 times -4 is -12. We write -12 here. In circuit diagrams, we sometimes call the nodes gates. So now let's zoom in a gate to preview how we'll do the backpropagation. So in the backward pass, we will compute the local gradient at each gate from left to right. And when I say local gradient, what is the gradient of the main function f with respect to the function in this gate? And we can use this mathematical notation to describe the process. Let's first focus on these two expressions and see how we use them to compute for the local gradient. Take note that dl over dz is the local gradient for this function, and dl dy is the local gradient for this function. In the process of backpropagation, we will be going backward through the circuit diagram, and so in general, we will already know the actual value of dl dz, and we'll be looking for the value of dl dy. For mathematics, dl over dy is simply the product of dl dz and dz dy. Since we already know dl dz, all that's left is to look for dz over dy. Now this node here on the right we will call function z, and this one on the left function y. And we get dz over dy by taking the derivative of z with respect to y. In general, you can remember to just take the derivative of the function on the right side of the arrow with respect to the function on the left side. And once you have that, you can multiply it to dl dz and get the local gradient dl over dy. Now, let's try backpropagating on our earlier example. Recall that these are the results from our forward pass. At the start of backpropagation, you always start with the end of the diagram and we'll be looking for the local gradient at this last node. So you'll be starting with the question like, what is the derivative of a function with respect to itself? This will always evaluate to 1. And we write down that value underneath our results from the forward pass. Next, we get the derivative of function f with respect to this intermediate function x plus y. In this step, you can choose to name the intermediate function or not, whatever makes the computation clearer for you. But here we named our intermediate function q, so q is equal to x plus y. And remember, we already know the local gradient of the node to the right, so we just multiply it by df dq, which is a derivative of the function on the right with respect to the function on the left of the arrow. So the derivative of f with respect to q is z. And from our given, z is equal to -4, and we multiply that by 1. And so we get -4. Okay, at this point we can choose to either solve for the local gradient at z, or we can branch out to the local gradients at x or y. So for now I'm going to go with z. And remember, we just need to take the derivative of f with respect to z and multiply that to 1. The derivative of f with respect to z is x plus y, and we know that x plus y is 3, and so the local gradient is 3. Great, so now let's branch out to both x and y. I'm going to start with x. And like the earlier steps, we're going to get the derivative of the right side function, which is x plus y, with respect to the left function, which is the variable x. And we're going to multiply that by -4. dq over dx is 1. And so we get -4 as the local gradient of x. Last few steps, we can compute for the local gradient at y using this expression. We get 1 times -4, and so the local gradient at y is -4. And so now we've found all the gradients of f with respect to its variables. Now what are these gradients supposed to mean? Let's take df over dx for example. This -4 value means that if I change x by some small number alpha, the resulting f will change by -4 times alpha. If I change y by some alpha, then f will also change by -4 times alpha, and so on. Let's demonstrate that. Suppose I change x by 0.5, so now my new x is -1.5. Let's get the new value of f. So -1.5 plus 5 is 3.5. Multiply that to -4, and we get -14. Remember, our old value for f was -12, and so from -12 to -14, the total change of 2f is -2, which is the same as -4 times 0.5. The same principle applies when I change my y or z by some small amount. Let's have a more complicated example. Here we have the function f given by this expression, and you have the values given for x, y, and z. Again, we're looking for the value of these partial derivatives. Breaking down the function into its most basic parts and in PEMDAS order, you can draw this circuit diagram. Let's begin with the forward pass. So 2 plus -3, you get -1. And doing these intermediate steps here, you get 1 and -1. To clarify what the operations in these nodes mean, this second node from the left is multiplication. This one is multiplication by -1, and this one is an exponential function. That means the natural number e raised to some number. And you can get these values above by applying the functions in the nodes. Now for the backward pass, we have these gates, and these are the results from the forward pass. We'll zoom in on the rightmost ones first. These expressions in boxes are the intermediate functions written explicitly so that we can more easily determine the derivatives. Again, we start with the derivative of the main function with respect to itself, which is always 1. Now let's evaluate the expression in yellow. As before, get the derivative of right over left. Let's write that out explicitly. This is 1 over a long expression, and below in the denominator we have the same long expression. So we can use this general formula to find the derivative. Using that, we get this whole expression. But we don't stop there. We want a numerical value. To do that, we plug in the original values of x, y, and z, and we get -0.53. Remember that we need to multiply that to a local gradient of the function on the right, and again we get -0.53. Let's write that down here. Here's a recap of what we just did. Feel free to pause the video to review. Let's move on to this section of the diagram. We found this number in blue previously, and we'll use it to evaluate the expression in yellow. Derivative of right over left. We get 1 plus a long exponential expression, and in the denominator we have the same long expression. So we can use this formula where the long expression will be our x. Going back, this evaluates to 1. We multiply that to the previous local gradient, and we get -0.53. Write the result below the arrow. Same process here. Note from e raised to -x plus y times z, the next expression in breaking the function down into simpler parts is negative quantity x plus y times z. This expression summarizes how we get the local gradient for this gate. Evaluating this derivative, I get e raised to -x plus y times z, and plugging in 2, -3, and -1 to get a numerical value, I get -2 minus 3 times -1. I get e raised to -1. Multiply that to -0.53. Actually, -0.53 is -0.5344 rounded off. I get approximately -0.2. And we write it here. Let's tackle the last part of the diagram. Zooming in, we see the local gradient we just computed. We have this expression for the local gradient. We can evaluate this to be -1, and we get +0.2 there. Here, the intermediate functions are broken down to even simpler ones. This local gradient corresponds to the node here, and this one to z. This evaluates to z, which is -1. This is x plus y, also -1. We end up with -0.2 for both nodes. Now let's branch out to x and y. These are the expressions for the local gradients. Both evaluate to 1. We get those. Now we've computed our circuit diagram with results from our forward pass and computed gradients from backpropagation. F is a kind of sigmoid function, so this whole chain is called a circuit for a neuron with a sigmoid activation function. Again, this means that if we change x by some small amount alpha, then f will change by -0.2 times alpha. If you know your calculus, you can actually do the backpropagation in one step. Here I have the solution for df over dx. Here's another for df over dy. And here's one for df over dz. But remember that as the neural network gets more complicated and has more layers, it gets harder and impractical to get the gradients in just one analytical step. Now that you have a general idea of how backpropagation works, you're ready for the next step in understanding neural networks, which is activation functions. To recap, backpropagation is the recursive application of the chain rule in order to find gradients, and computational graphs make it possible for us to visualize the process. To create the computational graph or circuit diagram, decompose the main function down into intermediate parts until you get to the basic variables. These will make it easier for you to derive gradients with the chain rule. After backpropagation, we know how much to increase or decrease our basic variables or weights in order to change our output by a specific amount. In general, you would avoid solving for gradients analytically, as this becomes impractical as the main function becomes more complex. Instead, backpropagate through the intermediate functions or nodes one step at a time. We'll see you in the next video.